Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Kumar Vishwakarma. I welcome you all to yet another session of VLearning. VLearning is a platform which focuses on providing right to quality education for all. Here, you get the entire course according to NCERT syllabus. We also offer VSMS, that is Vista Smart School Management System. It is an amazing application. This is for all the schools, all the colleges, all the universities, all the educational organizations out there. This tool enables the management to handle complex tracking and teaching processes very easily. To know more about it in detail, you can log on to www.dreammitra.in. And for our students, you can log on to www.vlearning.in, v-learning.in. Alright, you can select your class, you can select your course, you can select your syllabus and you can start studying. Along with the live classes there, you will get notes for each and every lecture. That's the best part. You will get animated videos for all the chapters. You will get condensed notes for the entire chapter, right, which will help you in the exam time as well. And you get assessment questions also, based on which you can assess yourself. Take part in the quiz. You will get the result on the spot. You will know where you stand in that particular chapter. And there are so many things in the web application. You can just go check it out, www.v-learning.in. Alright? And for our YouTube viewers, we have already started live classes from class 1 to 10. So just go see our videos. If you like them, like it, subscribe to our channel and click on the bell icon to get regular updates. And share it with your friends, family and relatives so that someone out there can get access to quality education. Okay? Alright. So without any delay, let's get started with today's session. Today we are going to do force on a current carrying conductor in a magnetic field. So this is lecture number 5. The previous 4 lectures, if you have not seen, the link is in the description. You can go watch it. Again, that is important from exam point of view. Then only if you attend those lectures, if you see those lectures, then only you will understand this. And this is important. Alright? Okay. So now we'll be seeing force on a current carrying conductor. When a current carrying conductor is placed in a magnetic field, what kind of force it experiences? So let's see, suppose this is a setup. There is a clamp. So here there is a rod. It is a conductor basically. Alright. So it is connected with a battery. See, this is the battery. Now this battery, the wire goes from this battery to this conductor, right? It connects one end of the conductor, then another end of the conductor is again connected to the battery. Alright. So when the key is on, the current flows like this. See, you can see the arrows. From here, then from here, B to A. Then from A again to inside the battery. Alright. Now what you have to do is, take a horseshoe magnet and bring it near. If you bring it near, now this magnet is having its own magnetic field. Magnets have the magnetic field, right? This magnet is also having its own magnetic field, and the direction of magnetic field will be from north to south, right? So this is north, this is south. So the magnetic field will be like this, upwards. This is the external magnetic field. This is, see, the current is flowing in the conductor, that's true. Conductor will also produce its own magnetic field, the concentric circles, right? Like this. But this is different, and this is external magnetic field which is produced by this magnet, alright? I hope it's clear. So now when the key was not on, the magnet was here, the magnetic field from the magnet was there. But the conductor was not getting attracted to it. Why? Because the conductor was not a magnetic substance and it was not having any magnetic field. Two magnets, why they do attract? It has a magnetic field, it has a magnetic field, right? That's the reason they both attract. Alright, so now this conductor, it was not a magnetic substance, it was not having any magnetic field of its own. So the moment you switch on this battery, the current starts flowing, and when the current flows in this conductor, magnetic field starts producing in this conductor. Correct? This kind of magnetic field. And now this is the external magnetic field because of the magnet, and this is the magnetic field because of the current, right? When these two magnetic fields interact, then either this rod will experience attraction or repulsion. Clear? So when the magnetic field is produced in this rod because of current and there is an external magnetic field, so what will happen? Either this rod will experience a attractive force or a repulsive force depending on the orientation of the magnetic field or the direction of the magnetic field. Alright? I hope it's clear. So now if I reverse, suppose, now see, this direction of magnetic field is upwards from north to south. Depending on the magnetic field in this rod or depending on the direction of current, there will be a magnetic field produced, right? Now suppose if it gets attracted towards this, it was like this, you brought a magnet, it became like this, somewhat. This is the magnet, the horseshoe magnet. This conductor is inside this. What happens the moment you switch on the battery? Depending on the direction of the magnetic field, this gets attracted, suppose. Fine. Now if I reverse this magnet or if I reverse the polarity, suppose if I make this as north and this as south, the magnetic field lines will be like this, right? So now this is the horseshoe magnet. If I reverse the polarity, this will go away. Clear? This will go away. So in this experiment, what was observed is by changing the direction of the external magnetic field, the direction of force changes. By changing the direction of external magnetic field, the direction of force changes. If earlier it was towards the magnet, then while changing the polarity, it will be away from the magnet. Clear? Another thing what they observed is by changing the direction of current, if we change this current direction, now battery is like this, the current is flowing in this way, right? And we know if we change the direction of current, the direction of magnetic field will also change, right? Not the external one, but which is produced because of this current carrying conductor, right? So the moment we change the battery, the current direction will be like this. The current direction will be opposite, right? Like this. And when the current will be like this, the magnetic field produced will be, remember the right hand thumb rule? This is in the direction of current like this. Earlier it was, the current was like this, so it was in this direction. Right now it is in this direction. Clear? Clockwise it is. Fine. So now when the current is reversed, the direction of force will also be reversed, because the magnetic field induced or produced by this current carrying conductor is also reversed. Got it? So understand the observations. First of all, when a current carrying conductor is placed in a magnetic field, the conductor experiences a force. This much is clear? Okay. Now the observations. On changing the direction of current, the direction of force changes. If earlier it was attracted towards the magnet, later it will, if you change the direction of current, it will deflect away from the magnet. Second, if current increases, force experience becomes stronger. We know if current increases, magnetic field strength increases, right? We have discussed this in the previous sessions. So if the magnetic field increases, the force also increases. If the magnetic field strength increases, then the force also increases. So that means force is directly proportional to the current. The more is the current, the more is the force. The more is the current, the more is the force. Understood? Second, what we observe? If we change the direction of the external magnetic field, the magnetic field due to that magnet, right? So on changing the direction of the magnetic field, this is the external magnetic field, the direction of force changes. Again, we observed that in that experiment. Alright? If external magnetic field increases, force experience becomes stronger. If you bring two horseshoe magnet, the external magnetic field will become more strong, right? So then the force experience will be more. If it was coming this much, it will go this much, right? The force will be more. Clear? That means force is directly proportional to the magnetic field. Magnetic field is represented by B. Magnetic field is represented by B. You will see it in your 12th standard. So for now, only these observations you have to keep in mind. This formula what we are deriving, this is not in your course, but for NTSC students preparing for their competition have to note it down. Then on increasing the length of the conductor, if we increase the length of the conductor, then also the force experienced by the conductor increases. Clear? Why? If the length increases, the magnetic field increases. Alright? The produced magnetic field inside the conductor increases, because of which the force experienced by the conductor increases. So force is directly proportional to L, length of the conductor. Okay? So that means, understand one thing. Now, if suppose this is the magnetic field, so this magnetic field will be denoted by B. This is the current, which is I, and this is the length of the conductor. Clear? So the force experienced by this rod will be directly proportional to B, to I, and to L. Let's see this. So now force is directly proportional to I, force is directly proportional to the magnetic field, force is directly proportional to the length of the conductor. If you sum it up, what you will get is force is directly proportional to I, B, and L. Alright? That means force is equal to K times of I, B, and L. And if you just match the SI units both the sides, what you will get is the value of K will be 1. And experimentally also it has been seen that F comes equal to the IBL. Alright, the value of this K is 1. So F is equal to I, B, and L. Clear? Now understand, this is the maximum force experienced by any conductor in a magnetic field. This is the maximum force experienced by any conductor in the magnetic field. Alright, actually force will be equal to I, B, L sine theta. Again this you will study in your 12th standard. No need to worry about it. I am just telling for your knowledge. F is equal to I, B, L sine theta. That is the actual force. This is the maximum force experienced by any conductor in a magnetic field. Note it down if you want. So what is this sine theta and all? I'll tell. See, force is a vector quantity, right? It has to have the direction. That's the reason the angles are involved. Let's go ahead. Now, force on a current carrying conductor in a magnetic field in different orientations. Now, suppose the magnetic field is like this. This is the external magnetic field. How this magnetic field can come? Suppose the horseshoe magnet is kept like this. This is north, this is south. So the magnetic field will be from north to south. Correct? So that's how you get the external magnetic field. Now suppose this is the external magnetic field, that is B. The length of the conductor, this is the conductor which is kept inside the magnetic field. L. And the current flowing in this conductor, let's say it is I. Alright. Another orientation can be, in this orientation if you see, this is 90 degrees. The conductor is kept at an angle of 90 degree with the external magnetic field, right? See everywhere. 90 degrees. Another orientation can be like this. This is the external magnetic field, this is the conductor, right? Again the same magnetic field is B. This conductor, the length is L. The current flowing in I. And this is kept at an angle with the magnetic field, right? So this angle, let's take this angle to be theta. Everywhere the angle will be same. This you have seen in maths. This is theta. It's only one angle, that is theta. Alright. Another orientation can be, now this angle can be any angle. You can move it. This is theta. Another orientation can be you have kept parallelly. One, you have kept perpendicularly to the magnetic field, that is at an angle of 90 degree. Second, you have kept parallelly. If the current is flowing like this in the direction of magnetic field, then this is parallel. If it is, suppose the conductor is like this and the current is flowing like this, then it is anti-parallel. Alright. In both the cases, this is parallel and anti-parallel. Clear? In these three orientations, understand this is important, in these three orientations, this is the orientation where the conductor will experience the maximum force. In this particular orientation, the conductor will experience the maximum force. Alright. How did we know this? Again from the experiment, but by the formula I will prove it to you. See, the formula what I told is IBL sine theta, correct? Sine theta, this theta is nothing but the angle between the conductor and the magnetic field. The direction of current and the magnetic field. Alright. This theta is the angle between this current is flowing in this conductor, so it is like this, right? And the magnetic field. So now here the angle is 90 degrees. If you put this theta as 90 degrees, sine 90 is 1. Sine 90 is 1. So now if I replace this by 1, F will be equal to IBL. That is the maximum force I told. Are yes or no? So this will be F max. Here the maximum force will be experienced by the conductor. Maximum force. Here if you see, the force will be minimum. The angle, if you see, the current and magnetic field, what is the angle between them? 0 degrees. The current is also in this direction, the magnetic field is also in this direction. So it is 0 degrees. Or if you see this one, the current is in this direction, magnetic field is in opposite direction. So this direction and opposite direction, it is 180 degrees. Right? So either the angle is 0 degrees or the angle is 180 degrees. If you put 0 here, sine 0 is 0. That means the force experience will be 0. IBL into 0 is 0. Right? So here the force will be minimum. Minimum force, that is 0. It will not experience any force. If you keep the conductor parallelly to the external magnetic field, there the force experienced by that conductor will be 0. Alright. Now here, since it is kept in some angle, so the force will not be maximum, neither it will be 0. Some force will be there. Force will not be equal to 0. But it will not be maximum also. Alright. Note it down. This is important. F is equal to IBL sine. Clear? So in the exam they ask when the force will be maximum, when the force will be minimum. In 10th level. If you go in 12th standard, the maximum questions will be from this particular orientation. Alright. So what you have to tell? If the conductor is kept perpendicular to the magnetic field, the force will be maximum. If the conductor is kept parallelly to the magnetic field, the force will be minimum. Alright. Let's get ahead. Fleming's left hand rule. Now again something very important. Now we have seen the force will be there. I was telling there will be attractive force or repulsive force. But how to get to know the direction of force? Every time we cannot go and do experiments, right? So now Fleming has given a rule. He told every time the direction of force will be like this only. Now Fleming's left hand rule, it indicates the direction of magnetic force if the direction of current and the direction of magnetic field is known. If you know the direction of current and if you know the direction of magnetic field, you can know the direction of magnetic force on that conductor. Clear? How? How? So the way we saw right hand thumb rule, that was right hand. So now this is left hand rule. Left hand rule. So what this rule says is, stretch the left hand such that the thumb, now this is left, the thumb, the first finger and the central finger are mutually perpendicular to each other. See, this and this and this are perpendicular, right? This and this are also perpendicular, see? See? This and this are perpendicular. This and this are perpendicular. And if you see this and this, the first and the third, again this and this, see. This is also perpendicular, right? This is like this. This is like this. Correct? All the three are mutually perpendicular to each other. So like this, you have to stretch your left hand. Now, if the first finger points in the direction of magnetic field, this is the first finger. If it points in the direction of magnetic field and the central finger points in the direction of current, this is the central finger. If this points in the direction of current, then this thumb will point in the direction of force. All right? See this. So this is like this. Force, magnetic field and current. So whenever you want to know the direction of force, just take your left hand. Put your first finger in the direction of magnetic field. Put your third middle finger in the direction of, or the central finger in the direction of current. Then wherever this thumb will be pointing will be the direction of force. Just make sure all these three should be mutually perpendicular. This should be like this should be like this. Now don't do like this. This is also mutually perpendicular, right? You don't have to do like this. It should be like this. Clear? This, then straight this, then this. Got it? Now how to remember this? Again, it's very easy. Force, magnetic field and current. How to remember that this is only force? This is only magnetic field, this is only current. How to remember this? Suppose if you forget and you make this as current and this, if you point this in the direction of current and this in the direction of magnetic field, then you will get the wrong answer, right? So to remember what my teacher told me, this is F, right? This is M, this is C, force, magnetic field and current. So now consider this as father, consider this as mother. Then after father and mother, the child comes. First the father, then the mother, then the child. And you can see the thumb is a bit thick than these two, right? So this will be the father. Then the mother will come, then the child will come. Alright? So if you remember like this, father, mother, child, you will know this is force, this is magnetic field, this is current. The first letter, F, M and C. Father, mother and child. Alright? You will never forget it. Okay? Now let's practice. Let's practice. Now suppose the magnetic field is in this direction. Alright, this is magnetic field. You can write B also, not a problem. And now suppose the conductor is kept like this. This is the current carrying wire or the current carrying conductor. And the current is flowing upwards. What will be the direction of force? Which side the force will, this wire will experience the force, which side? We need to understand this, alright? Now, again, let's write it current. Fleming's left hand rule. The first finger in the direction of magnetic field, like this. So first of all, make it like this, mutually perpendicular. First finger in the direction of magnetic field, second finger, this central finger in the direction of current. Current is upward, right? This should be up. This should always be here, whatsoever. This should always be here. This in the direction of current. Now see the thumb. Where is it pointing? Where my thumb is pointing? It is pointing inside the board. If you do it in your notebook also, just make this. You will see your thumb will be pointing inside the notebook. Right? So that means this wire, it will experience the force towards inside. It's like someone is pulling it from inside. Like this, the force it will experience. And inside, how do we show inside? I already told you in one of the sessions. Inside means like this. If you want to show inside, see, if you want to show right, we show like this. If you want to show left, we show like this. If you want to show up, we show like this. If you want to show down, we show like this. But there are two more directions. That is inside and outside. How do we show that? How do we show that? If you want to show something is going inside, you have to show it with this cross. And if you want to show something is coming outside of this board, you want to, or outside of your notebook, you have to show it with a dot. All right, this is inside. I'll write separately. I'll write. Inwards. Outwards. All right. Inwards, outwards. Now, so that means this is the direction of force. Inwards. Okay. Clear? You can show like this. This is force. Force is inside. The wire is experiencing the force inwards. Clear? Now, let's take another example. Suppose if I reverse the direction of current, let's do this. Now, if I reverse the direction of current, can you tell which side the force will come? The wire, this conductor will experience the force in which direction? Take it out fast. How to do it? You know it. Fleming's left hand rule. Apply it. Did you get the answer? Did you get the answer? Is it coming outwards? Let's check. So now first, like this, magnetic field. This one is magnetic field. So this finger is pointing the magnetic field. Current, downwards. Now the moment I pointed this downwards, my thumb is pointing outwards. My thumb is pointing outwards, right? So that means the force will be outwards. It will be someone is pulling this wire like this. Clear? So that means the force experienced by this wire is outwards. This is the current. Or I'll write. Force is outwards. Understood? I hope you are getting it. All right. Note it down. Now let's see one more. Now this time I'll try to make some 3D diagram. All right. Now suppose a magnet is kept like this. Another magnet is kept like this. So you can see. Now if this is north and this is south, the magnetic field will be like this. Correct? Now suppose the wire is kept like this. I hope you can understand, this is 3D, this wire is inside. Now this is the direction of current. This red one is the magnetic field. What will be the direction of force? Tell me. This wire is going inside the board. The current is going towards inside the board. The magnetic field is in this direction, not to south. What will be the direction of force? Again, let's find out. See, magnetic field in this direction. Current, or I'll do it from here only. Magnetic field in this direction. See this? Current is inside. Magnetic field is in this direction. Current is inside. So the magnetic force downwards. So the magnetic force is downwards. That means this wire, I will show it with this color. I hope you can see it. It will be pulled downwards. This is the direction of force. Did you understand? If the current is inside, the magnetic field is in this direction, the wire will be pulled downwards. The force will be downwards. Clear? You can try with different orientations in your notebook. I am giving you a homework. Note it down. Suppose this is one magnet. This is another magnet. The magnetic field, okay, this is a bit down I have made. Alright, the magnetic field this time is again, this is north, this is south. And the wire, this time it is kept like this. Alright, 3D, if you see the wire is coming out of the board, I hope you can understand this. The wire is coming outside the board. The magnetic field, you have to draw the direction. I have just told this is north of the magnet, this is south of the magnet. And you have to comment me the direction of force. This is current. Alright, take it as homework. This one. This last one is for homework. Noted? So now we know how to find the direction of force when a current carrying conductor is kept in a magnetic field. Now let's understand one more thing. Again, this is important. Force on moving charges in a magnetic field. Force on moving charges in a magnetic field. Till now we have seen force on conductor in a magnetic field, right? Now force on moving charges. First of all, charges are of two types, positive, negative, and one more is there, that is neutral, right? So positive is current we take as positive, right? It is not a charge is proton, alpha particle, like that, there are a lot. Current I have written because we take it as positive. Current is in opposite direction of electrons, right? We take the direction of currents when towards the direction of the protons, right? We assume that if electrons are going in this direction, the protons or the positive charge is going in this direction, and we take the direction of current towards that, right? That's why I have written positive. Current, proton and alpha particle, negative, electron and beta particle, and neutral, neutron and gamma particle. So now here in this, when the conductor or the current was going, what is actually flowing? The charges. What is actually flowing? The charges. The force is actually experienced by the charges, right? So that means here if you see, if the current is going upward, the negative charge is going downwards, right? So now if I give you a question, in spite of telling that there is a current, if I tell you the negative charge is going downwards, tell me the direction of force. Can you do that? If the negative is going downwards, take the direction of current in the opposite direction and put this Fleming's left hand rule. Alright. If I tell you there is a positive charge which is going upwards, in the same question I am not telling you current, I am telling if a positive charge, there is a magnetic field like this, if a positive charge is going upwards, what will be the direction of force? Again you can use the Fleming's left hand rule. In the direction of positive charge, you have to point the direction of current. Clear? Let me make it easy for you. Now, suppose, now you know inward and outward, right? Suppose there is a magnetic field which is inside. This magnetic field means going inside the board. I'll remove this circle, it is not looking good now. Now suppose this is a magnetic field. If I tell you there is a positive charge which is going like this. This is the magnetic field. Can you tell the direction of magnetic field? Inside the board. The magnetic field is going like this, inside. Alright. Now there is a positive charge which is going, I am throwing a positive charge, let's say E plus. I am throwing it inside this, like this. What will happen? The moment I throw this inside this, there is a force what I have put on this, alright. Now this is going inside. Or let's say it is going with a constant velocity, doesn't matter. If it is going inside, the direction of this positive charge is this, and the direction of positive charge and the direction of current is same. Are yes or no? The direction of positive charge and the direction of current is same. So this is the direction of current, and the direction of magnetic field is this. Magnetic field is inside, current is this. See, current is this, magnetic field is inside, so the force will be towards up. So the moment it will enter this magnetic field, this will go like this. Because now this is experiencing a force upwards. It will not go straight, it will go like this. Now if I throw a negative charge in this same direction, in the same magnetic field, tell me what will happen? Magnetic field is inside. Negative charge, if it is going in this direction, what is the direction of current? Is it not the opposite direction? If the electron, if the negative charge is coming in this direction, the direction of current will be opposite to the direction of electron. Alright, so you have to do the same thing. Magnetic field inside, the direction of current here, this side. Magnetic field is inside, or I'll try like this. Magnetic field is inside. The direction of current is this side. Correct? Direction of current is opposite. Electron is this side. Direction of current is opposite. So if the magnetic field is inside, direction of current is this. See the direction of force. Downwards. Right? That means this electron, the moment it will enter this magnetic field, it will come down. Clear? The moment this electron will enter the magnetic field, it will come down. I hope now you understood this. It's interesting. Note it down. So if positive and negative comes, you'll understand negative charge, if it is there, you have to take the direction of current in the opposite direction and use the same Fleming's left hand rule. Force, magnetic field and current. If positive charge is thrown, take the direction of current as positive. Take it in the direction of current. Take the same direction as the direction of current. Alright. Now suppose if a neutral thing is thrown. If a neutral, suppose a neutron I have thrown like this. So when you throw a neutral thing inside a magnetic field, it goes undeflected. It goes undeflected. It will not deflect. Alright, if I throw a neutron inside a magnetic field, it will go undeflected. Clear? Now, there is a small homework for you. Now, suppose this is a magnetic field. Can you understand this magnetic field? So this is the magnetic field. How is it? It's coming outward. From inside it is coming outward, right? Now, so there is one particle which went like this and it went like this. There is another particle which went like this. There is another particle, I hope you can see, which went like this. Alright, I'll make this properly, no? Now you have to tell, this is a homework. You have to tell in the comment section which is positive, which is negative, which is neutral. Alright, this time the magnetic field is outwards. Note it down, note your homework. So let's go ahead. Fine. So in this session, it was till here. I hope you understood it. The force on a current carrying conductor when it is kept in an external magnetic field. Right? Now you know the formula for force. You can calculate the magnitude of force, and now you can know the direction of force as well. So now this particular thing we will use in electric motor. In the next session, we are not going to see electric motor, chill. In the next session, we are going to see questions and answers discussion based on previous sessions. We have done so many sessions, 5 lectures are over, but we have not discussed question and answers yet, right? So in the next session, we will be discussing it very properly. Good questions I will bring for you. Okay, till then,